Okay, we're going to continue on here. Chapter 12 sounds like a chapter, maybe. So we're talking about kinetics in this chapter, and last time we talked about what is sometimes referred to as the rate expression. And the rate expression really allows you to sort of figure out in a reaction how reactants or products are basically changing over a period of time. If we had just a reaction like so here, we could write a rate expression, and the rate would equal, remember, we're going to go with negative here, 1 over the coefficient. And again, that does take care of the stoichiometry, as we talked about, the mole-to-mole relationship, the change in the concentration of A over the change in time. That would also equal the rate, I'm sorry, that would also equal 1 over 3, which is the coefficient there. Again, here on the product side, it's going to be positive. We don't need the negative, as it should be increasing with time. And we'll have the change in the concentration of B over the change in time. So you can write them all together. Again, you can write them individually, like I almost did here anyways, but we'll do it this way. Or you could have the rate is equal to 1 over 3, change concentration of B over change of time. So once again, as we talked about, pretty much if you know really just one piece of information, maybe you know the average rate, or maybe you know how A is changing with time or B is changing with time. That's pretty much all you need to then figure out how everybody else in the reaction is changing. So again, if we happen to know how A is changing with time, that would allow you to calculate the average rate. That average rate there is the same as this guy, which then you could use, obviously, to calculate how B is changing with time. Remember, as we talked about, that the average rate for the reaction should be a positive number. But if you're talking about how a reactant is changing over time, you will probably end up with a negative number in terms of how it's changing as it's decreasing with time. And if you sort of calculate how products are increasing with time, you'll end up with a positive number in that particular case. Um, we then got into sort of at the very end there, rate laws, and that usually looks something like this. And a rate law is a little bit different than the rate expression. The rate law deals with really just reactants. And we don't include products typically in our rate law. We also have these X's and Y's. These guys are what are referred to as the orders. And the little k here is our rate constant. And again, that is the constant value that you have in a reaction at a particular temperature and the way it's written. So remember, as we also talked about, that these are really going to be found sort of experimentally. So when we talk about X and Y, they're the orders. They are not from the coefficients in the balance equation or anything like that. So they're not like equal to, say, these guys. You do have to sort of experimentally determine those guys. You can add them together. X plus Y, for example, would give you the overall order of that reaction. So that is something else that we can sometimes do here. So we can use these, as we talked about, I think, at the very end last time. Again, if you sort of know the rate law, you also know sort of the orders of each reactant, which again are sort of the proportion at which they need to react to sort of generate a particular rate. You can use that to your benefit to, as we talked about, either maybe slow up a reaction, you could actually speed up a reaction. So you could kind of play with it. And depending on the order of the individual reactants, some may have a greater effect on the rate if you do something to them than others. So as we saw at the end there, right, if we had somebody that had, say, an order of 0, you could do whatever you want to that guy. It's not going to affect the overall rate of that reaction, as opposed to somebody that has, say, a second order for it. It would obviously have a greater impact, say, on the rate than somebody that had a first order in terms of the reactant. So knowing those things can allow you to sort of manipulate the reaction and maybe make it as fast or slow as you want. Any questions on that stuff there we talked about last time? Okay, so speaking of this, what do you usually sort of get in terms of how you would calculate that stuff? So again, if we had like a reaction here, actually we'll do this, plus B goes to C. Typically in these situations, you will be given a table, and in that table will be some concentration of your reactants. You will also be given kind of the initial rates, and that'll be like molarity over seconds. And usually in this, you'll be given a number of sort of trials or experiments. Could be 3, could be 4, 5, 6, could be a ton of different sort of experiments. And you'll have sort of the concentrations, say, for each. I would just kind of go with those for now. All right. So what you want to do, actually, I'll just get rid of that experiment. I'll just do 3. So what we want to do when we look at a sort of table like this is we want to use this, and this is typically experimental information, again, that would be given to you. And what you want to do is analyze the information that's in the data to help you really determine the orders for everybody in these particular reactions. Now, you can do it just looking at it, but most people maybe can't do that, and that's probably not a great way to do it in here since you should show your work anyway. So you really should take more of a mathematical sort of approach is probably the best way to do that. So the way that we could do that is we could use sort of a formula like this where we take rate 2 over rate 1 equals k to the a to the x, b to the y, and k a to the x and b to the y. So when we see here rate 1 and rate 2, it doesn't mean that you go to the table, for example, and just choose entry number 1 and 2. It just means that you need to go to the table and pick two sort of experiments from the table and use that information. Now, how should we pick which ones we want to do? So we'll start with our generic rate law, which if we wrote for this would be something like the rate is equal to k a to the x and b to the y. And again, here, the goal is to try to figure out what x and y is in this case. And when we go to this table, we really want to have as little unknowns as possible, right? So what we're looking for is 2 reactions or 2 entries in this table where one of the reactants stays the same and the other one varies. And that's going to give you really only one unknown at a time. If you happen to have 3 reactants, you would do 2 reactants to stay the same and one varies. So the idea there is to just have one that's different, and that will only give you one unknown that you need to solve for. So for example, if I look at experiments 1 and 2, we would see that the concentration of A stays the same, but the concentration of B actually varies. And that would be good here. Now, the other thing I would recommend is when you find the 2 that you want to look at in terms of the table, I would personally pick the one that has the larger rate and put it up on top. And you don't have to do that. It just gives you kind of nicer whole numbers at the end. It makes it a little bit easier to sort of just visually look at it. If you do it the other way, it will come out the same. But usually if you kind of pick the larger rate and put that one up on top, it'll kind of yield you some nicer whole numbers that you kind of look at. So what I'm going to do is I'm going to take and look at here experiments basically 1 and 2 in this made up example. We'll see how I did. And I'm going to put everything from experiment 1 up on top because, again, it has kind of the larger rate. So that's going to give me 6 here, molar seconds, is equal to k times my 2 to the x and my 4 to the y. And again, this is basically everything up on top for here. That all comes from experiment 1. I'm going to do the same thing for experiment 2. So up on the bottom there, we're going to have 3 molar seconds is equal to k. Again, my molarity here going to be 2 to the x and 2 to the y in this particular case, right? So if we look at this point, we can now just do some math. So if I divide that out, that is going to give me a 2. Now, at this point, when I come over here, that little k is the rate constant, which means it is the same number or different numbers on top and bottom. should be the same. It's a constant, right? So those guys, although we don't know what it is at this point, it should cancel out. Now, the x here, which is the order with respect to A, should also be the same on top and bottom. Again, we don't know what it is at this point, but we do know it should be the same, which means really that's going to cancel out as well. And then now we basically have 4 divided by 2, which will give me 2 to the y in this particular case, right? At this point, I can now solve for y, and again, with these nice pretty whole numbers here, I could see hopefully that y is equal to 1 in this case. And that would give me my order with respect to b in this particular case. Now, by the way, if you don't have pretty numbers or you can't visualize this result, and sometimes they're not nice pretty numbers like this, obviously, one way you could do it is you could just natural log both sides. And that will bring the y down and then divide the natural log back to the other side. So if you kind of natural log both sides, that'll get you there as well. So if you don't have really pretty numbers, or if you accidentally, or maybe you did it, you did the kind of smaller rate up on top, you'll get more of a decimal number. So it might not be as maybe common to you to see what the result would be. Again, you could natural log both sides and then divide it out and solve for whatever you're looking for. Any questions on that one there? Now that we did that, what we then want to do actually would be to go back into this table. And we want to go back into this table. And now in the first time around, we kept A constant. This time around, we actually want to keep B constant. So if we do that, I'm going to look at B, and I can see in experiment 2 and experiment 3, B is constant, while A is varying in this particular case. So I'm going to look now at experiments 2 and experiments 3 to do this. So looking at experiment 2 and 3, again, we're going to kind of use that formula. We're going to use, in this case, the rates are the same, so it don't really matter which one you do. So we'll go with 3 is equal to k, and I'll do experiment 3 up on top. That'll give me 4 to the x, 2 to the y, divided now by what we have in experiment 2 here. We have 3 is equal to k, 2 to the x, and 2 to the y. So now again, we can do this. Again, everything up on top is experiment 3. Everything on the bottom there is experiment 2. We do that. That gives me a 1. Once again, the k's here should cancel. Our 4 divided by 2 here will give me 2 to the x. And here our y's should also cancel. In this case, right, something that equals 1 to the 0 power, right? X would equal 0 in this case. Again, that's how you get to 1. And that would give me the order here with respect to A in this particular case. Any questions on that? Now that I've used the data in this table to actually figure out the orders, I could actually write my completed rate law, which is the rate would equal K. And in this case, it would actually be B here. Now, I could also write, if I wanted to, we'll do rate is equal to K, A to the 0, and B. That's okay as well. Can I write the rate is equal to K A times B? Is that okay? That is not okay, because with nothing written there, it's implied that that is actually 1, right? So that would not be okay. So in this case, if you happen to get a 0 order, you do need to put the 0 in if you're going to include it in the rate law. You can also exclude it from the rate law because it basically equals 1 as well. So you could do it either way. Any questions on that there? Now that I actually have the rate law at this point, what I could actually do now is use the rate law, because I now know the orders. I could actually use it to solve for what the value of the rate constant is. So I can now, for example, if I wanted to rearrange my rate law and go, my rate constant would equal the rate divided by B. Now, where can I get those numbers? I get those numbers also from the table. So it does not matter which one you choose. You could choose experiment 1, experiment 2, or experiment 3. They all should yield you the same rate constant. Again, you can't mix and match, so you got to choose everybody from one experiment or two or three and put it in there. Any questions on sort of that there? All right, so why don't you try here? Let's see here. Why don't you do this one, and why don't you figure out the completed rate law with the orders? Figure out the overall order as well of the reaction, and also figure out the value of the rate constant. All right, so using that information there, see what you come up with. Okay, so let's take a look and kind of see how you're doing and progressing. So here is it's very common, like I said, in these type of problems, you'll be given a table. In this case, again, we have 3 entries, but sometimes, like I said, you may have a table that has multiple and more entries in this. And it doesn't really matter how many entries you have. You really want to take the same approach. So I would always kind of start with just the generic sort of rate law and just kind of write out what we're looking for. Remember that it only includes the reactants. So those are really the ones that we're kind of trying to find here. So our rate law kind of looks like this. And we want to figure out, again, the orders first using the information that's given to us. Once again, no products in the rate law. So looking at the table, we can see actually here again in experiment 1 and experiment 2, the concentration of F2 stays the same while we have some variable sort of concentrations for our other reactant. And that's essentially what we're looking for. Again, we want to kind of use this sort of generic formula here to solve for this, picking again 2 entries from the table where one of the reactants stays constant and the other one varies. And as I said earlier, if you happen to have 3 reactants, then you would want to do 2 stays the same and 1 varies. So in this case, looking at experiments 1 and 2 in this case, like I said before, I'm going to go with the larger rate there up on top. So I'm going to put number 2 up on top because it does have the larger rate. That's going to give me 4.8 times 10 to the minus 3 there is equal to K times my concentration there of 0.1 molar to the X and my other concentration of 0.04 molar to the Y. So once again, everything here is basically from experiment number 2. I'll do the same thing here for experiment number 1, and we'll go with 1.2 times 10 to the minus 3, our K 0.1 to the X, and our 0.01 to the Y in this case. Now doing our sort of math here, that's going to give me 4. Once again, don't know what the value is, but it should be the same for the rate constant. Don't know what the value of X is at this point, but it should be the same for both of them, which means they should cancel out. And again, that's going to give me, I think, a 4 to the Y. Once again, you could probably just obviously see that Y is equal to 1. But again, if you're not sure, just natural log again, both sides and kind of divide it out and it'll get you there. Now that I did that, I now want to really kind of switch it around and I want to keep, in this case, the ClO2 constant while I vary the other one. And it looks like I could achieve that here in experiment 1 and experiment 3. Our guy there stays constant. So we'll look at experiment 1 and 3 to get the other order there. And doing so, again, I'm going to pick experiment 3 to go up on top as it has the larger rate. So that, again, that should give me a little bit better whole numbers. As I also mentioned earlier, you don't necessarily have to do that. You could do it the other way. You'll just get more decimal type numbers, but it does work out the same. So again, up on top is everything from experiment 3. On the bottom there, going to go with experiment 1. So dividing out gives me 2. Once again, these are going to cancel. That's going to equal 2 to the X. And again, these are going to cancel as well. And here we get X is equal to 1 in this case. Now that we've got the individual orders for each of the reactants, we could write our rate law. Our rate law in this case then would be K, A, and B in this case. And that would also mean that the overall order can again be found by adding the individual orders together. So in this case, our overall would be 1 plus 1 is a second order reaction. So overall, this reaction is second order. At this point, we now can, as I said earlier, use our completed rate law to figure out the actual value of the rate constant. So if I take my rate law I just found and I actually solve for the K, which is our rate constant, that would give me rate is equal to A over B, basically. As I mentioned before, at this point, you really can choose any of the entries in the table. They should give you the same value. I'm just going to go with experiment 1 and put that information in. That will give me 1.2 times 10 to the minus 3 molar seconds divided by our A, which is 0.1 molar, and our B, which is 0.01 molar. Now, if I do that there, my calculator maybe turns on 1.2 to the minus 3 divided by 0.1 divided by 0.01. Going to give me 1.2. Now, in terms of units, the molarity up on top will cancel with one of the molarities on the bottom. That will give me basically 1 over molar seconds. Or you could write m to the minus 1, s to the minus 1. However you want to do that is fine as well. And the units here, the rate constant, are actually the common units that you see for a second order reaction overall. And that's really important, as we'll talk about later on in this chapter. Sometimes they won't tell you the ordered reaction, but they'll give you the value of the rate constant with the units. And from those units, you could actually determine what the order of the reaction is. And that's very common for second order reaction to have 1 over molar seconds or something like that. Yeah. Are you talking about here at the end, or are you talking about? Yeah, you should if you're given, so you should if you're giving the answer for the rate constant, it should have units. And typically speaking, if you're asked to rate the rate law overall, it would probably be something like this. If you're asked to get with the proper orders. Be using units here, although sometimes I don't use it here, but technically in there you should have units. But I'm going to give the answer for constant should have units. The rate itself should have units if you're asked specifically for that. I would say in general, what you're asked to give on these type of problems is like an answer sort of like this, just kind of more of a generic one with the actual orders, and give the value of the rate constant or something like that, and that would need units associated with it. Yeah. Other questions? So definitely for the rate constant, definitely the units should there, because they're really important, because they do tell you again sort of what order the reaction is and stuff like that. Other questions? Yeah. So as we just saw, the rate law are always determined experimentally. And once again, those orders are not equal to the coefficient in the balance equation. Can they end up being the same number as what you see in the balance equation? Yes, but that's again not how you get those. You do have to do sort of the calculation and figure out the orders from them. They're not just equal to coefficient, as in the case we just did. That was coefficient 2, but actually the order there was 1 for ClO2. Yeah. All right. So once you do this one, the rate equation for the reaction NO is the rate's equal to K NO times O3. If the rate is 6.60 times 10 to the minus 5 molar seconds, when the concentration of NO is 1 to the minus 6. Okay, so in this case, they actually gave us the rate law. We didn't have to calculate it. So the rate here is KNO03. That would mean, again, not written there, the order with respect to NO is 1. With O3, it is also 1. Not also asked here, but the overall order here would be, again, 1 plus 1. Again, this is going to be a second order reaction. Here we can just solve for K by dividing that to the other side. So K would equal the rate divided by NO and O3. Put in our numbers. They did give us the rate 6.60 times 10 to the minus 5 molar seconds divided by our NO, which is 1 times 10 to the minus 6 molar, and our 3 times 10 to the minus 6 molar as well. That is going to get us here, making sure you use your exponent buttons for sure. It's like 2.20 times 10 to the 7, looks like. Again, in terms of units, molarity on top and bottom will cancel, giving us what we saw in the previous one, 1 over molar seconds. So as you can see, also second order, also the rate constant ends up with the same units here of 1 over molar seconds. Any questions on that there? All right, so let's try another one here. Let's do the rate law again and the orders, the overall order, and the okay, so let's take a look again. We wanted to choose two entries where we keep one the same. So 1 and 2 here, we'll do that for our first one. And obviously that's going to vary our second one there. I'm just going to erase this here. Just a little bit of space here. All right, so starting with our rate law, we should have, obviously in this case, just our reactants. So the rate's equal to K S2O82 minus to the X and I minus to the Y. Looking at experiment 1 and 2, I am again going to kind of choose the larger rate one to put up on top, just give it nicer numbers. So 2.2 times 10 to the minus 4 molar seconds divided by 1.1 times 10 to the minus 4 molar seconds would equal RK, and we got 0.08 molar to the X and 0.034 molar there to the Y, divided by on the bottom our 0.08 molar to the X and our 0.017 to the Y. So again here, we're going to divide, and that's going to give us a 2. These guys will cancel. Once again, the X's should be the same, so they will completely cancel as well. And also a 2 there, I think, to the Y. Once again, you could probably just see that Y will equal 1 in this case. Again, like I said before, you can natural log the 2 on the left. You can't see it, and natural log over here will bring this down. And again, you can divide it back out the other way if you needed to. All right, now that I did that, we're gonna go back to the table so we could get the other entry there. And in this case, we're gonna go with 2 and 3. That's gonna keep the I minus constant. So experiment 2 and 3 here. Again, going to go with experiment 3 on the top, as that has the larger rate. And again, should give me a little bit better whole numbers there. So we'll put in all of our stuff here for entry 3. And for entry 2 here, 1.1 times 10 to the minus 4 molar seconds. We got our K, our 0.08 to the X, and our 0.017 and to the Y. So it's going to give us a 4. Once again, this is going to cancel here. We're going to actually get a 2 to the X, and these guys will cancel. Again, you can hopefully see X is going to equal 2 in this case, which would be our order with respect to our first reactant there. That's going to give us our completed rate law here. Basically, the rate is equal to K times the S2O82 minus, and that is to the second, and our I minus here to our first. First off, any questions on the calculation there? Yeah. At this point, we could also do the overall order. And again, the overall order here is going to just be adding that up. That's going to be a 2 plus 1, which is actually a third order reaction in this case. At this point, we can now use our completed rate law to figure out the value of K. K will equal the rate divided by the S2082 minus squared and the I minus. You do need to square it here. So again, that's also something people will kind of forget to do. Once again, as I mentioned, you could actually choose any of these entries. So just for fun, we'll do number 2 this time. And we'll put in our values there. So our K will be our 1.1 times 10 to the minus 4 molar seconds divided by our 0.08 molar. And that again going to be squared. Divided by our 0.017 molar, and that is just going to be what it is there. We will end up with 1.1 to the minus 4 divided by 0.08 squared divided by 0.017. Looks like a 1.01. Now, in terms of units here, molarity on top, we'll cancel one of the molarities on the bottom. The others will actually stay there. They'll actually end up with 1 over molar squared seconds in this case, yeah? Or again, you could do m to the minus 2, s to the minus 1 as well. Question on that there. We also see different units for the rate constant here for a third order versus what we saw previously there in the last couple for a second order, right? By the way, if you count up the units, that's an m and an s, that's 2, a second order. Count up the units here, that's m squared and s, that's like 3 letters, so that's like a third order maybe. Yeah, this could be how it works, I'm not sure. Any questions there? All right, a couple more to figure out our orders first, and from the orders we could obviously get our rate constant values. So we'll start with just a generic here, and again just our reactants included. In this case we got 4 entries, so I'm going to go with 1 and 2 here, and that will keep our second guy constant and vary our first. So this will give me, I'm going to actually go with number 2 up on top there. So it has a little larger of a value. Experiments 1 and 2. So that will give me 0.0082 molar seconds is equal to K times our 0.2 molars to the X and our 0.1 molar there to the Y. Now putting everything from experiment 1 up on top, 0.0021 molar seconds. Our K, our 0.1 molar to the X. Put the X on the outside. That'd be good. And our 0.1 molar to the Y. So doing a little dividing in this case, 0.0082 divided by 0.0021 can actually give us a 3.90476. I'll call it. That's going to cancel. These guys here are going to get us a 2 to the X, and then these guys should, at this point, completely cancel. Now, again, at this point, you do not have a nice, pretty perfect number there. That is pretty close to 4. You can natural log our 3.90476 equals the natural log of 2. When you do that, the X comes down. Divide the natural log of 2 back over there. And if you do all that good stuff there, you will end up with about an X value of 1.97, and that's going to probably be close enough to 2. You could alternatively probably did the 3.9 to 4 and did a 2 as well. But again, just to show you, sometimes the numbers don't come out really pretty and perfect, whole numbers. So again, that is how you would get there. Now that we did that, we would go to our other one to keep it constant. It looks like we have one option for that to keep that guy constant. Speaking of that, we actually had more than one option for the first one. We could have chose some other entries as well. So for example, before we move on to this one, We could also did, for example, 1 and 4 would have been a perfectly fine as well. So again, just to show you, it doesn't really matter which one you choose. If we did experiment 1 and 4 and did the same calculation, we would end up with 0.033 molar seconds equals K, our 0.4 to the X molar, and our 0.1 molar to the Y. And we would have our 0.0021 molar seconds, our K, 0.1 molar to the X, and 0.1 molar there to the Y. In this case, we would end up with 0.033 divided by 0.0021. You're going to end up with a 15.7142 is equal to, these guys will cancel. This is actually going to give you a 4 to the X, and those guys would cancel. Once again, here we would natural log the 15.71429 really is equal to the natural log of 4 to the X. Divide the natural log of 4 back over. And again, as you can see, not a really perfect whole number in this case either, but it should in the end get us to a X value of 1.99, which again is 2. So again, it doesn't matter which one that you choose. You can choose multiple ones. They all should give you the same one. Yeah. What was that? Yeah, in this case, this is experimental and it's pretty darn close, 1.99 or 1.97. That's pretty close to 2. I would round up to a whole number in this case. So again, also, we actually had a third option as well. We could also done 2 and 4 as well, and obviously you would get the same answer. So again, if you have more than one option in these tables, in this case, we actually had 3 options to figure out the order with respect to NO2. You could choose any one. They all should give you the same. You don't have to do all 3 of them or all 3 options. But again, just to kind of show you. All right, now that I overdid that one, let's actually go back to the other guy there, and then we're going to do experiments 2 and 3 for our other one. And I think I'll just erase maybe the bottom there. Just do it there. So I'll switch the page. All right, so now looking at experiments 2 and 3, really to get the other order. We will have, looks like it doesn't really matter too close, but we'll go with number 3 up on top. 0.0083 molar seconds is equal to our K, our 0.2 molar to the X, our 0.2 molar there to the Y. And putting in our other guy there, 0.00, we got there 82 molar seconds, our K, our 0.2 molar to the X, and our 0.1 molar to the Y. Once again, if you do that, you got pretty close to 1 in this case. You actually get a little bit over. It looks like 1.01 is equal to, these guys will cancel, these guys are going to cancel, and that's going to give you basically a 2 to the Y. As we've been talking about, basically something to 1 is going to be our 0 order for this particular guy's question on that. You also, again, could natural log both sides, and you'll get basically a 0 there on the other side. And when you divide it out, you'll basically get 0 as well with some rounding. At this point, we now have our completed rate law. In this case, the rate would equal our KNO2, and this is going to be squared. Once again, I'm going to choose not to include the other guy. If you do include this guy, again, you do need to put the 0 there and not just leave it with nothing there. That now will allow us to get to our rate constant by rearranging this. And if we do that, here, we'll just get rid of some right here. There's a little spot there to pop that in. All right, so rearranging the rate constant here, that's going to give us K is equal to the rate divided by our NO2, and it is going to be squared. I'm just going to pick the first entry there. So that'll give us 0.0021 molar seconds divided by 0.1 molar. Again, we do need to square it. That's going to get us 0.0021 divided by 0.1 squared. Going to give us a 0.21, I think there. 0.21. Units here, again, molarity on top. We'll take out one of the molarities on the bottom, 1 over molar seconds in this particular case. In terms of the overall order, it obviously is 2 plus 0, which is second order. And once again, you can see we're back to the units that we saw previously for a second order. And again, that's a really important sort of thing to tie together the units of the rate constant and the overall order. Any questions on those calculations there? Yeah. To figure out the rate constant is there. Yeah, you could use, technically speaking, you should be able to use them all and they all should come out the same. Yeah. Again, you just can't mix and match. So if you choose to use the first one, you got to use all the information for the first one. You can't like pick and choose parts of each. So got to be completely all the information for any of the experiments. Other questions? Okay, one last one here. Now that we're professionals, there we go. Same deal. Okay, so let's take a look here. So again, we're going to try to figure out our orders and everything. And we're looking for the order for NH4 plus and for NO2 minus. So again here, you could choose whichever combination you want. I'm just going to looking at, obviously you can see 1 and 2 is going to get that guy constant on the right there. Look at those. Here I am going to, once again, go with the larger number up on top just to try to get a little bit better whole numbers. So experiment 2 is going to go up. That's 0.3, by the way, times 10 to the minus 7. And hopefully you didn't miss that in the table. Otherwise, it might make a difference later, I'm imagining. You got 0.06 molar to the X, 0.2 molar to the Y in that case. Now, putting everything here for experiment 1, 10.8, also times 10 to the minus 7 molar seconds. K are 0.02 molar to the X, are 0.2 molar to the Y in this case. So doing a little dividing there, that's going to give us basically 2.99, which is pretty close to 3. It's equal to the K's will cancel. That's going to give us a 3 to the X, and those guys will completely cancel. And here X would equal 1 in this case. Any questions on that? Now, if you kind of missed that times 10 to minus 7, the right answer at this point. Just later on, you will not probably have the right answer, just so you know. We could then go to 3 and 4. That remain constant. And we'll do our same thing here. We're going to take, in this case, it looks like 4 up on top. It has the larger value. So we're going to go 21.6 times 10 to the minus 7. Bad sign. Is 2 molar to the X and 0.0404 molar to the Y. Dividing it out here, 10.8 times 10 to the minus 7 molar seconds. RK 0.2 molar to the X and 0.0202 molar there to the Y. Here, dividing out 21.6 to the minus 7 divided by 10.8 to the minus 7. Gonna get us a 2, looks like in that case, which is good. Okay, cancel. These guys obviously cancel in here. That's going to give us a 2 to the Y. So Y is going to equal 1 in this case. That will give us our rate law here of our rate is equal to K NH4 plus and NO2 minus. That means that our overall order is going to be 1 plus 1, which again is second order in this case. And now we can actually solve for the value of K. So K will equal the rate divided by NH4 plus and NO2 minus. Once again, you can choose any of the entries, so why not just go one? This is the part, if you miss that times 10 to the minus 7, that you're going to have the wrong answer. Divided by 0.02 molar and 0.2 molar. Here we will end up with looks like over here 2.70 times 10 to the minus 4 units, molarity on top. There are again n to the minus 1 or s to the minus 1, however you want to write it. Well, question on any of those steps. So again, if you missed this, you'll be okay because they divided it out here, so it all worked out okay. But here they did not, so that would obviously not be good. Yeah. So you want to make sure also when you look at these tables that you also look at the headings and make sure you don't have some type of abbreviation like that as well. Any questions on how to figure out the rate law, how to figure out the orders, the value of the rate constant? All right, professionals, I like it. All right, we'll lay it up there. I think for today, we're going